So we're going to kind of pick up where we left off with the osmosis lecture, and we learned about hypertonic, hypotonic, and isotonic and how water moves, okay? And today we're going to be learning about water potential. And so water potential is basically explaining why water moves the way that it does. Okay, so why does it move this way? What's happening here? How can we even figure out if something's hypertonic and hypotonic anyway? Like, how do we know that? Because like I can't see that stuff. It's actually dissolved to microscopic, right? These pictures, of course, like in real life, we don't have cartooning, right? We're just looking at like a beaker of stuff. How are we supposed to know? The answer here is water potential. Okay. So what water potential is it is the force that is responsible for the movement of water in a system. You can think about it as water's potential energy to perform work. And it seems weird to think about water doing work, but it does. Okay. The symbol for water potential is psi. That's how you say that. It kind of looks like a trident. That's how I remember it, trident ocean. Okay, like Poseidon. And then we've got two different units here for water potential. It's measured in bars most commonly, or megapascals. 1 megapascal is equal to 10 bars. You'll see how more of that works later. But let's take a look at these two beakers here. This beaker has pure water. This beaker has some, let's say, salt in it. So this beaker with water, just pure water, the water has nothing to do because there's nothing in it. So there's nothing for it to dissolve. So the water is just sitting there. It has all the time on its hands because it has no work right now. So it has a lot of potential to do work because it's not busy. It's totally free, wide open. Whereas over here, this beaker that has the salt in it, some of this water is starting to work to dissolve the salt. So some of this salt water is busy doing the dissolving. Okay, so some of this water here is at work, whereas this water here is totally available. So water potential is the measure of the free energy of water, which is less when it has solutes to surround, aka things to dissolve. So let's go back. Which water has more potential energy? Well, because this one has nothing in it, it has all of the water is free to do work, so it has the most potential energy. Whereas this water, some of it is already working to dissolve the salt. Some of it isn't working to do that yet. So some of it's free to do work, some of it isn't. So this beaker would have less free potential energy. Okay. So if you can imagine here, the most free energy possible for water is in pure water. Okay. So when we're talking about pure water, it's going to have a water potential of 0. Why? Because 0 things are dissolved in it. And so we have all of our water available to do work. However much water is there, doesn't matter. It's all available to do work. So our highest water potential value is going to be 0 because you can't get any more pure than pure water. So highest is 0 and everything else is going to be negative. You cannot have a positive water potential. It doesn't exist. All right, so water potential, this is an equation. It's on your AP Bio sheet. It is determined by two things. It looks scarier than it is, okay? It's a simple addition problem. It is determined by how much solute is there, right? How much dissolved stuff, and how much pressure there is in the solution. And so here's water potential. You take how much solute plus pressure, add them together, you get your water potential, okay? So now we're going to look at each one of these factors individually, the solute potential and the pressure potential. All right, so this little psi with an S is called solute potential. And basically all it is it's how much stuff is there. How much solute is there in the water? A little bit or a lot or medium? How much? We measure this in moles or molarity with a capital M. And so the more solute there is, the M value increases. Okay. You might remember this from chemistry, some of you all, with molarity. So the higher the molarity, the less free water there is to do. So as you get a higher molarity, your solute potential is going to decrease. It's going to get more negative again because there's less free water available to do work, and our highest is 0. Okay. So it's always going to be a negative number unless it's pure water, and then it'll be 0. Next up is our pressure potential. This is coming from the pressure on like the water, okay, as it's moving. So this can be positive, negative, or 0. Positive would be either water is actively flowing into the system or water is contained and pushing against something. Like in our example back with our cells, like right here, this would be a positive pressure potential with our water pushing against that plant cell. Okay, that would be a positive. Negative would be when it isn't all full and water can possibly move into a space. That would be negative. And zero would be whenever water is exposed to air. A lake, a stream, a river, an ocean, an open beaker or glass of water would all have values of zero. And so the reason why we do this is we're going to use this to help us figure out which way water is going to move if we have like a cell in a liquid, okay? We can calculate the water potential of the liquid and the water potential of the cell, and water is gonna move from an area of high water potential to an area of low water potential, okay? So water always falls from high to low. So let's take a look at this now using our equations, and I think hopefully you'll see it's not so bad as it may seem. Don't let those symbols freak you out. Okay. So we've got a plant cell. It's got a pressure of negative 0.3 and a solute potential of negative 0.1. So what's the water potential? Okay, so I'm solving for this, which means I'm going to add my two other numbers. Here's my solute is negative 0.1. Here's my pressure, negative 0.3. I'm going to add them together. And what do I get? Negative 0.4. Boom, that's the water potential. Easy, right? Let's look at another one. Here I've got a cell. I'm told the water potential is negative 0.2 and the solute is negative 0.1. So here I'm finding the pressure potential. So this time I'm solving for the P value here. I was given this one and this one. So if we plug those into our equation, we would say negative 2.2 is equal to negative 0.1 plus pressure. I'm gonna I'm going to subtract negative 0.1 from both sides. And when you subtract a negative, it's like adding to be a positive. So you end up with negative 0.1 equals the pressure. Example number 3. Okay, we got 3 plant cells stacked on top of each other. C is negative 0.5, B is negative 0.2, and A is 0. So which direction would the water flow? Water flows from high to low. Where's our high? Actually, cell A is our high, right? It's 0. So water is going to move from A to B up to C. And this is actually how water moves in trees. This is how water gets from roots to leaves. The leaves have a low water potential. The roots have a high. Moves on up. Here's another example. Okay, we got a cell in a beaker. The cell's water potential is negative 1.5 and its pressure is 3. And the sugar water has a solute of negative 0.4. All right, so here we're going to figure out what is the cell's solute potential. All right, so let's figure out how we could make that work. Well, we're going to be using our equation down here. We know that the water potential is negative 0.5. We're solving for the solute. It told us that the pressure is 3. So we're going to subtract 3 from both sides, and that's going to give us negative 4.5 bars as the solute potential. Our next question be what is the sugar water's pressure potential? Okay, so this sugar water in the beaker, well, it's going to be 0 because a beaker is an open container and that's automatically 0. No real math to do there. Isn't that nice? Okay, what is the water potential of the sugar water now? Okay, so water potential is the solute plus the pressure. Well, our solute, it tells us, is negative 4.5. We just figured out that the pressure is 0. So negative 4.5 plus 0 is negative 4.5 bars. And then lastly here, which way will the water move, into or out of the cell? So let's take a look. The water potential of the solution is negative 4.5. The water potential of the cell is negative 1.5. So which one is higher, negative 1.5 or negative 4.5? Negative 1.5 is higher in negative number land, right? So water is going to move out of the cell. It's going to move from that negative 1.5 to the negative 4.5, from high to low. One last equation for you, and it has to do with this value right here, the psi with an S, solute potential. You can calculate it, right? Just what you always hoped for. And this is also on your AP Bio equation sheet, and the solute potential is negative I CRT. Whoa. Okay, so I is an ionization constant. It's going to be either 1 for sucrose or 2 for salt. You'll be told that. Those are like the only 2 things that you're given. And so that's what you get for that. C stands for the molarity. Okay, so like 1 mole or 0.5 moles or whatever. R is a pressure constant. A constant means it never changes. So this is going to always be 0.0831. And T is going to be your temperature in Kelvin. And to get that, you do 273 plus your temperature in degrees Celsius. And once you do all this math, all of the units cancel out to give you an answer in bars. Okay, so let's take a look. What is the solute potential of a 0.1 molar solution of sucrose at 22 degrees Celsius? We're using negative ICRT. I for sucrose is 1. R is going to be 0.0831. And then we're going to need to do 273 plus 22. So here's what that looks like when we plug it in. Negative 1 times 0.1 times 0.0831. And then when I get 273 plus 22, I get 295. So I multiply these 4 values together and I get negative 2.45 bars. So here are all the things to consider for both the osmosis lecture and the water potential lecture. We will be doing lots of practice problems in class, so you'll get some more practice with this. And hopefully if you're still feeling a little shaky on the math, I think it'll make a lot more sense once we do it in class. And here's where things are in the textbook.